If you want to transition from writing basic CRUD applications to building massive, high-throughput systems that handle millions of concurrent users, or if you're preparing to crush your next system design interview to land a senior role with a significant pay bump, mastering these core concepts is non-negotiable. System design is what separates junior coders from senior engineers who understand how to keep complex applications fast, fault-tolerant, and resilient under heavy traffic. In this video, we are breaking down 20 essential system design concepts, covering everything from networking and API architecture patterns to database scaling and distributed message queues, all explained clearly in just 10 minutes. Vertical scaling. Imagine starting with a single server fulfilling requests for your application. As traffic grows, the simplest way to scale is upgrading hardware, adding more RAM or a faster CPU. This is vertical scaling. It's simple to set up, but quickly hits hardware capacity limits. Horizontal scaling. A better approach is adding server replicas to split the workload. This is horizontal scaling. It enables near-infinite scalability using commodity hardware, eliminates single points of failure, and adds fault tolerance, though it increases architectural complexity. Load balancers. With multiple servers, how do you prevent one server from overloading while others sit idle? A load balancer acts as a reverse proxy, distributing incoming traffic using algorithms like round-robin, request IP hashing, or geographic routing. Content Delivery Networks, CDNs. To serve static assets like images, videos, HTML, and JavaScript globally with low latency, you use a CDN. A CDN is a network of geographically distributed proxy servers that cache assets from your origin server and serve them from the closest node to the user. Caching. CDNs are just one form of caching, storing copies of data so future requests are fulfilled faster. Caching occurs across every system layer: browser disk caching, in-memory caches like Redis, and hardware CPU caches, L1, L2, L3. IP address. How do computers communicate across networks? Every device is assigned a unique IP address, which serves as its destination identifier across local networks and the global internet. TCP/IP. Data transmission is governed by protocols like TCP/IP. Data is broken down into small packets, transmitted across the network, and reassembled in order. TCP guarantees packet order and retransmits missing packets, providing a reliable base for HTTP and WebSockets. Domain Name System, DNS. Users don't memorize IP addresses. They enter domain names like google.com. DNS translates domain names into IP addresses using records like DNS-A records, which are then cached locally by your operating system. HTTP. HTTP is an application layer protocol built on top of TCP, following a client-server model. A request consists of headers, metadata like origin and content type, and a body, payload, with the server responding in a similar structure. REST APIs. REST is a widely used API architectural pattern built around HTTP. It is stateless and relies on standard HTTP methods and status codes, such as 200 for success, 400 for client errors, and 500 for server errors. GraphQL. Introduced by Facebook in 2015 as an alternative to REST, GraphQL allows clients to request exact data fields in a single query. This avoids overfetching data and eliminates multiple round-trip requests.
gRPC. gRPC is a high-performance RPC framework developed by Google for fast server-to-server communication. It uses protocol buffers to serialize data into binary formats rather than JSON, reducing payload size and network latency.
WebSockets. Unlike HTTP's request-response cycle, WebSockets establish a full duplex persistent TCP connection for real-time bidirectional communication. It's ideal for chat applications and live data feeds without polling.
SQL and Relational Databases. Relational databases like PostgreSQL and MySQL store structured data in rows and tables. They utilize optimized data structures like B-trees for rapid data retrieval using SQL queries.
ACID properties. Relational databases enforce ACID compliance. Atomicity, all or nothing transactions. Consistency, rules strictly enforced. Isolation, concurrent transactions don't conflict. And durability, persisted data survives system crashes. NoSQL Databases. To overcome scaling limitations of relational databases, NoSQL databases trade rigid schema consistency for seamless horizontal scaling. Popular types include key-value stores, document databases, and graph databases. Sharding horizontally partitions database tables across multiple independent servers using a shard key, like user ID, allowing database workloads to handle massive scale.
Replication. Replication duplicates data nodes for read scalability and fault tolerance. In leader-follower replication, writes go to the leader and replicate to followers. Leader-leader replication allows writes across multiple region nodes.
The CAP theorem states that in a distributed network experiencing a network partition, a database system can guarantee either consistency, all nodes see the same data, or availability, every request receives a response, but not both simultaneously. Message queues. Message queues serve as asynchronous buffers between decoupled application components. They persist incoming tasks so worker processes can execute heavy workloads asynchronously without overloading main services. And that covers 20 essential system design concepts. If you want to dive deeper and get detailed step-by-step breakdowns for each of these topics, make sure to subscribe to the channel and follow our dedicated system design and microservices playlists. Also, all the diagrams and slides shown in this video are shared via a link in the description below, so you can reference them anytime. We regularly release comprehensive tutorials to help you master architecture and crush your tech interviews. Thanks for watching, and I'll see you in the next video.